All right. Hello and welcome to the second to last week of classes. So I don't want to bombard you with new information that I'm going to test you on. So I have created these slides so that I can teach you about some things that I am very interested in and that I think will help you as you progress as a computer scientist. So the title of these slides are Lambda Calculus and Programming Language Semantics, and I love both of these topics. I'm not going to test you on any of this. I am just here to indoctrinate you. Are you ready? So it's kind of like a cult, and this is your initiation. Okay? So you have probably read in your textbook, there's a chapter on, or a section of a chapter on Turing machines, right? And that's one way to model computation. You have like a tape that can be read, that can be like shifted along, and you can write things to each element of a tape. And that sounds like it's all, I don't know, 70s, or I guess it was invented back in the 40s, right? It sounds old school. Like, we don't want to deal with tapes. We want to deal with, I don't know, mathematical structures, right? Enter this thing called the Lambda Calculus, okay? It actually is just as powerful as a Turing machine. Just as powerful. No different. Equivalent to a Turing machine. If only I could spell equivalent. And if you remember reading that Turing machines model any computer that ever has existed or ever will exist. Okay? Anything that you can compute using a Turing machine. And I'm telling you that this thing called the Lambda Calculus is equivalent in power to a Turing machine, and so it can also represent any possible program that you could ever write or ever hope to write. Okay? And this one's fun. A bit more fun, in my opinion. Okay? And one really good reason for me to want to teach this to you right now, if you're not really interested in just being a member of this cult, but actually getting something out of this lecture and the next one, pretty much every language these days, including C++, including Java, including like the ones that people really use, they have support for these things called lambdas, right? So it's not just Racket at the end of the day. That has a lambda inside of it. So I want to teach you about where they came from, and you should get a bit better at writing anonymous functions, at least, by the end of these slides. Okay, are you ready to dive in? All right, so the idea of the lambda calculus, we're representing computational things that we can compute. Actually, we can get away with representing just functions, okay? Everything in the lambda calculus is a function. A number is a function. True or false, that's just a function, okay? It's weird, but it works, and I'm going to show you why. I'm going to prove it to you. So here is the simplest possible function you could ever hope to write. It's you read it as lambda x and then x. This dot is like a separator. It's like and here's the body, okay? That's the idea. So this is like the lambda part. It introduces a variable, okay? We also say binds, and binds the variable x. Okay? So it's lambda, and then you say the variable name that you're about to bind. Okay, it's your parameter name. It's the parameter of the function. Okay? And then you have a little dot, and then you have the body of that function. Okay? So it's just one thing in the body right now, but that is the body. Okay, that's the function. That's all it is. Lambda x, x. You give me an x, and I return you back x. That's all it's doing. Okay? That is the idea. And notice, first of all, it's an anonymous function, just like the ones we've been talking about in Racket sometimes when we use like filter and things like that. It has no name. It's just a function, and you can immediately give it something to apply to. Okay? That's the idea. And to apply the function, you just put something right next to it. Okay? Just put the thing next to it to apply it, okay? So for example, if I want to apply this function, lambda xx, to the number 5, all I have to do is put the 5 right here, okay? It's like saying, okay, please apply this function to this argument. Here's the function, here's the argument, okay? And what happens is this is ready to be reduced, okay? This can be reduced through reduction to applying this function. It's like, okay, this is a function that essentially looks like this in C++. It's like return x. That's all it really is, right? And so we gave it an argument. Let's apply it by substituting 5 for x in the body. That's what we do. We just substitute. Subst. That's all you have to do to evaluate a Lambda Calculus program. You just substitute things in the body and make sure that you don't like overwrite anything, but we'll get there. So really this, okay, how do you, so it's like x with 5 substituted for x. That becomes, okay, please let's replace this body with 5 every time we see x. Okay, 5, that's the answer. Isn't that cool? So what is this function? Do you know what it is? Is there a name for this? Maybe if you've taken what is it, linear algebra, you'll know. It's the identity function. It's the identity function. You give me an x, I give you that same x back. Okay, so it's this function, f of x equals x, or in C++ land that. It is the identity function. Cool, huh? And so we have this in Racket. So here in Racket, we can just do this immediately. We can just say lambda like x with, I don't know, it gives back x. That's how you do it in Racket. And then we can immediately apply that function to a number, like 5. Cool, huh? Give it 42 and give it high. Whatever it does, it just returns back what you give it. That's all. So that is how you do it in Racket. You have to use some extra parentheses. That's all. Okay, isn't that nice? This is recording, yes. So yeah, that is the identity function in the Lambda calculus. Let's see what else. What else? One thing that you can do is also apply it to itself. And I noticed that I just wrote this in the wrong spot, sorry. That should go right there. If you have a function, I mean, it can take any argument. There's no types involved here. So here's what we can do. Watch. Lambda x, x. Please apply yourself to lambda y, y. And so all it does is, okay, I'm applying this function to this argument. I'm just going to substitute this whole thing in for that, okay? And so we get, well, I can give it the same one too. These don't matter. And so, oh man, that becomes lambda xx again. It gives itself back. It gives its first argument back. Isn't that cool? You can apply it to itself. And the idea of binding is all the same for all in there exist. You have free versus bound variables. So for example, I know I'm running out of room here, so maybe let me make a blank slide just to drive the point home. Lambda, oh no, I don't want any design ideas, thank you. Lambda xx is equivalent to lambda yy. It's equivalent to lambda zz. It's just the argument name. That's all. As long as you change it everywhere, it's fine. And these are all bound. X is bound, y is bound, z is bound, because they are parameters. Okay? They take those parameters. It's possible that you have some constant sticking out somewhere. Like somewhere else you've defined y, and maybe this function disregards x and returns y back. This is an example of a free variable. Y is free. Okay, so I hope these ideas from the quantifiers are coming back to you. So this one hopefully gets substituted somewhere else, because right now it's just a variable. It's sitting around, it's not bound. That's all. Okay? That is the idea of free versus bound. And so that's the Lambda calculus. All you have to do is write a bunch of functions for everything. I'm going to show you how. And that is how we do our stuff. So how about more exciting functions, though? This is probably the most simple function that we could ever write in the Lambda calculus. It just returns its argument. How do we do more? How do we write a function, for example, of 2 parameters? Because that takes more than one argument. because all we have to do, like the shape of all the stuff that we write in the lambda calculus, it's always lambda and then a variable name and then a dot and then some body. You can write variables here, you can apply them, apply functions, make new lambdas. This is what everything has to look like in the lambda calculus. So if you want to make a function with more than one parameter that takes more than one argument, I guess to be precise, I should say parameter here, you just have two lambdas. Yeah? So this is like, technically the parentheses are going to get drawn like this. Whee! But you can leave them out. So it's just a function that returns another function that then is ready to take the next argument. That's all. Okay? So let me show you this in Racket. We can do, I don't know, lambda x, take the first argument, and give back lambda y that takes the second argument and maybe adds the two, xy. See that? That's what we can have. We can have these functions just like this, okay? And then when we apply this to something, it takes both things, right? The first thing, if we just apply like 4, that's not enough arguments, right? It's not enough. It's only gonna, okay, it's gonna have replaced the x. That's all. So I wonder if I can show you this. Racket this. Yeah, so it's still, when I apply it to 4, it's still giving me back a function because it hasn't finished yet with this lambda. Because this should give back, just substitute in everywhere for x in this inner lambda. It should give back lambda y plus 4y. See? So this, if you partially apply it, it's like the plus 4 function. We'll get there in a second. So we need to finish it off. So maybe I can have 4 and 2. So I got to apply the function that I get back. Okay? 4 and 2 perhaps, and that will give me back 6. Yay. There it goes and gives me back 6. Because now it's applied the 4, so it's given me back the next lambda. And then finally I apply the 2 to that lambda, and now I have actual values for x and y. So let me show you how this is working on the slides, and that should make it make a bit more sense. Okay? So yeah, if you just want 2 arguments, just make 2 lambdas. So lambda x, lambda y, x plus y, assuming we have a plus sitting around somewhere. We can apply this to 2 things. We can apply it to 4, and then we can apply it to 2, okay? And it kind of, the parentheses get drawn like this. So the first thing that happens is whenever you have a lambda and you apply something, you apply an argument to a lambda, you substitute. You substitute 4 in the body, where this is like the body, for the x, okay? This gets substituted for x. So watch what happens. This is the body. It is lambda y, x plus y, and we're substituting 4 for every x we see, okay? So instead of x, we have 4. Isn't that cute? And then we still have the 2 to apply. So applying 1 is ready to accept the other one. It's another function ready to take the second argument and then finally do the plus. Okay? I hope you see that. Please yell at me if you have any questions about this. I'd be happy to talk about it. I love this stuff. And then finally, we have the 2 to apply to this lambda, which is going to substitute in this body the 2 for the y. Okay? So this will give me back 4 plus 2, and that'll eventually like get evaluated to 6. Yeah, that's the idea. And this process of, instead of making a function with 2 parameters, making a function that returns another function that's waiting for that second parameter is called currying. Okay? It's named after a famous mathematician whose name is Haskell Curry. Okay? And there's also a programming language called Haskell that is functional and cool. So yeah, that is the idea. That's how you make functions with more than one parameter in the lambda calculus. You just make a second lambda. Yeah? So this might seem like weird and maybe kind of cool, but maybe you're still wondering about how in the world do we actually compute any possible computation with just functions and application? Well, do I have a section for you? Let's do this. So here I am defining a bunch of things, okay? Whenever you see this, it's like I am about to define this as this, just to make it easier on ourselves, okay? That's all. So true, let's define it as a function that takes 2 arguments and returns the first, okay? This is where it gets fun and cool. So true is just a function that takes 2 arguments, x and y, and forgets about the second and returns the first, okay? That takes 2 args and returns whatever you give first. Okay? This is how we can make true and false in this language. Okay? And this one is just a function that takes 2 arguments and returns the second one. Dot, 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 and returns the second one. Okay? That's true and that's false. Let me prove to you that this is actually useful. And like, this is going to work. Because it blew my mind when I first learned about all this stuff. Just functions and application of those functions. We can make anything. We don't even have to give the functions a name. It's crazy. Here is and. Here is the and function. It's a weird one. It takes 2 things, right? Those 2 things that you want to and together. And then it applies those things in weird ways. Okay, so it takes P and Q and it's supposed to give back. It's meant to give back P and Q somehow. And I'm going to prove to you that it works. Okay, and then we'll get to the others. So, and then it starts using P and Q as functions. Okay, starts using P and Q as functions. At least P as a function. Crazy, huh? Okay, let me prove to you that this actually does and. Let me do and of true and false. Okay, so it's and of true and false. And I'm going to substitute everything now. So this is going to take a second. So this is equal to, equivalent to, okay, so and lambda P, lambda Q of PQP. And then I have to give it true and false. Okay? So true is take 2 things, give me back the first thing. False is lambda x, lambda y, give back the second thing. And just with this, you actually make a working language. And when you apply functions like this, it's always the parentheses start going inwards to the left. And so this is how you draw those parentheses. So this is the full computation. And let me prove to you that this ends up being false, right? Because true and false should be false. Let me prove this to you. It's crazy. You can do this for everything. Okay? There's a way to encode it all. So the first thing that happens is, okay, the first argument that I'm about to apply into is called P, okay? So I'm going to replace this for P in this body. In this body. Because it still needs to take that second parameter. Okay, so this is going to be replacing P, okay? Are you ready? So, okay, we can do that. So it becomes lambda Q, and then we replace P with this argument that we gave for it. Lambda X, lambda Y, X. Okay, sure. And then Q, and then lambda X, lambda Y, X. And so there's our result of the substitution. And then we still have this to apply at the end. That was our false, right? Lambda X, lambda Y, Y. Okay? Following that? So let me give myself slightly more room. We are getting to the end here. because now we have to do a few more substitutions, right? We have to apply this function. It would make the most sense to apply this function now to this big one, which is waiting for a q, and then it's going to do all this stuff. Okay, so we're going to replace this for q, okay, in this body here. Okay, so this replaces q, and it becomes, and I'll probably need a new slide, and it becomes, let's see here, lambda, it's this thing first, we still have that, lambda x, which was true, right? Lambda y x, and then the q that I'm substituting this for. Let's see here, lambda x, lambda y, y, and then I have this true all over again. Okay, sure. And then we have lambda x, lambda y, x. Okay, so this is almost the end, because we have to just apply these functions now. You see that in this order? This is like the first function, and we apply it by putting our parentheses in this way. Are you ready? Because we're going to end up with false, assuming I didn't make any silly mistakes. Let's do it. And hopefully this is the first of many examples to blow your mind. All right, let's evaluate this. Let's continue. So, okay, what needs to happen now? We have a function application. That's all there is in Lambda Calculus, functions and applying them. So we have this guy to substitute for, it looks like the x. Okay, this is a function that's waiting for its first parameter x. Okay, and so here's its body. And so in that body, we're going to replace this for the x. And it's okay for us to introduce a new x because we're about to replace the old one. That'll be okay. That should work. Dun, dun, dun. But sometimes you have to watch out and like make this one a z instead. But we're good for right now, I think. So this becomes now lambda y. It's the body of the original function, which was itself a function, as usual. Lambda y dot x. And then we're going to replace that x with that body there. So it's like this, lambda x. And then now we do have a problem, okay? So how about I just change this one to something equivalent, because we already have a bound y. We can't introduce a new y. That is a no-no. So let's make this something different. Let's change all the variables to something brand new and fresh. Okay, so let's, instead of calling this lambda x, lambda y, y, it's just as easily, it could be called lambda, let's not use p and q, I don't know, lambda a, lambda b, b. Just returns its second argument. That's all it is. Okay, let's have that one. Let's make it that one. Okay, and so now I'll replace this for the x. So it's lambda a, lambda b, b. Okay, so this is now my big long function. It takes 3 arguments now. You see that? It's waiting to take 3 arguments. I can get rid of those parentheses. And so now the only thing that's left is this guy that we're applying on the right. Lambda x, lambda y, x. Are you ready? So just to get ready, let's make sure, let's just change all these variables around to like c and d or something. This is equivalent to lambda y, lambda a, lambda b, b, and this is equivalent to, let's make it c and d, lambda c, lambda d, c. Okay, now we don't have any same parameter names, and that is better. Okay, we don't want to capture any variables. That's the problem that could happen. It's called capturing. And so now, okay, where are we applying this function? Okay, what are we doing? So this guy needs to come in for y. It needs to be replacing y in this body here. So every time we see y in the body, this replaces it. There is no y. because some of these trues and falses, they forget about their parameters. And so now that's what's happening. It's forgetting about this y. We don't use it anymore. And so this is just this. See that? This becomes lambda a, lambda b, which is a function that forgets about its first parameter and returns the second. What is that equivalent to? We can change the variables around again if we want to. Lambda x, lambda y, y. What is that? Which one is that? Oh man, it was false. So hopefully that helps to prove to you that there's actually something here, okay? I encourage you to try it for true, because it works. I promise it does. Okay, so you can do the same for or, and sorry, I didn't label this properly. Look at the slight difference. This is take two arguments p and q, p, q, p. This is p, p, q. That ends up giving you or, okay? It's something about, okay, see if one was true. If so, we can continue. Okay, but again, you're applying functions to themselves. Okay, that is the idea. And so it really does work. That is the idea. Okay, so that's or. I encourage you to try it for or. I think it would take a bit too long. How about I try this one in Racket? Okay, let's try it in Racket. Okay. Are you ready? So let's build some things up, I guess, is the idea. We're going to have to define some things. So let's say that define true, that is, it's a function that returns, takes two arguments, x and y, and returns x, lambda x, lambda y, and it returns the x. Okay, that's true. And then false is something that returns the y instead. Okay, that's true and false. And then we can do or. Dun. And so maybe I should like say true lambda, false lambda, because I think I'm overwriting a lot of things that I might need later. Let's do or lambda. That is, takes two arguments, p and q, and does ppq. Are you ready? So it takes two arguments, so it's lambda p, lambda q, and then it returns ppq. And the way that it's defined, it has to be special. So first we apply the p to the p, and then we have the q at the end. I want to introduce, oh no, it's not letting me. Silly. I think that should do it. We'll try it. So, in theory, I should be able to say something like or lambda. Let's apply or to true and false. Okay. And it needs to be applied in this way with the parentheses going like this. It still doesn't like that. Silly Racket thinks I'm insane. So that, unless I got it backwards, that should do it. And so this actually returns back a function, and luckily for us, it gives us back its name, which is true. Isn't that cool? And if I replace this with false, guess which one it's going to return? Or let's actually do it like this. It works. It really does work. Or false and false. That's the only time you get false. Isn't that so cool? So that's or. You can do not. Not is just, okay, take your true or false and apply false to true. Okay? P, false, true. So here's what we can do. We can say not of true. That expands to lambda p, p, I'll just do f and t, because why not? And we apply that to true, which is lambda x, lambda y, return back the first thing. Look what happens. So this is just saying, okay, replace this for p. So lambda x, lambda y, x, and then we have ft, And guess what's going to happen here? It's going to take its 2 parameters and give back the first one, the false. See how it's working? Isn't that so cool? And so we get back false. Not of true is totally false. It totally works. And then we can do if then else's. We can be like, okay, if, so this is like the predicate. So this is the Boolean. You apply it to the Boolean, and then you give it 2 things to do. This is the true case, and this is the false case. And because these predicates, true and false, are just functions, it's like, okay, if it was true, it's going to do the first thing. If it was false, it's going to do the second thing. That's why it works. Isn't that so cool? Okay, let's keep going, because there's so much more. It's all so much fun. Okay, now it's time for numbers, right? We would like to make numbers in this language of just functions and applications. So let's ask something philosophically that we haven't asked yet really in this class. What is the number 5? Like, what is a number? We have so many symbols to talk about 5, but what is it at the end of the day? How can we define it? Okay? And the way that we will define it in the Lambda Calculus is it is 5. It is defined to be we're adding 1 to 0 5 times. Okay? That is how we will define 5 in the Lambda Calculus. That's how we will represent every possible natural number. And we have to do it a bit more trickily because we can only have functions, but it's going to work. Okay? So the natural numbers, they are functions of 2 parameters. Think of this like a struct definition, kind of. The 2 parameters are just fill-ins for ideas, okay? Each parameter is an idea. The first parameter is the idea of +1, okay? Each param, so they're just functions. We'll have them represent an idea. The first, which we call S, will be the successor, or +1 function. S is the successor, which is the +1 function. And then Z is not a function anymore, but it's just the object 0. It's the idea of 0. Okay? So, how do you represent 0 as a function of 2 parameters? One, the first being the idea of adding 1, and the second being the idea of 0. Well, 0 is just give back the 0 bit. Yeah? Take those 2 parameters as you would, and 0 is the answer. That's how we can define the number 0. It's just iteration of a function. So we don't iterate it at all, we're stuck at 0. And now for 1, it takes those 2 parameters that have the idea of being the +1 function and the idea of being 0, and then we just apply that successor function, +1, to 0. That's all it is. 1 is just adding 1 to 0. See that? Starting from 0, apply this idea of the successor function. Okay? Same for 2. Take those 2 parameters as you need to, and then apply the successor function twice to 0. See that? And 3, apply the successor function 3 times to 0. It adds 1 3 times, in essence, to 0. And so that's how we can make 5. Okay? And the coolest thing now is that we have immediately access to numbers. Okay? Numbers and operations. We can define plus now. Let me show you plus, because why not? It's awesome. Okay, let's make sure I have enough space. Plus, what's that going to be? Well, it's going to be a function of, again, a bunch of parameters. These are the things you want to add, m and n you want to add. And so the idea of this is it gives back m plus n. It's meant to give back m plus n. Or the idea of it, okay? In this encoding of the natural numbers. So it takes those 2 numbers, takes the 2 numbers, and then it does some fancy work. Because again, it needs to give back a number, so that number needs to start with this, and then it does some stuff. Oh, oops. F was something that I forgot to replace. Okay, sorry, I fixed it. It was supposed to be an S. So this is what's going to happen. It's going to give back m plus n, and you can do the same for multiplication and power computations. So let's quickly do 2 plus 2, right? Let's make sure that this can do 2 plus 2. So it's plus, and then we have 2 twice, and s lambda z, and so it's s of z. That's 2, and we're going to do that twice. Oh no. There we go. Okay, and so I'll go a bit faster this time. So this is going to associate like this. We're going to insert this for the m in this body here. Okay, so it becomes lambda n, and then we have lambda s, lambda z, and then we have m, n, z, and sc. Okay, so this needs to be replacing, what is it? The m. Okay, so it looks like m is only there once. We're going to replace that there. And we run into the capture issue. So let's rename. Let's rename all our variables. This is now going to become not that, but like, I don't know, lambda x, lambda y of x, x, y. Okay, that'll make it easier on us. So we'll replace this in for m now. So here's our m, lambda x, lambda y, x, x, y, in that order. And then, let's see what else. Then we have to give the rest of this body. It's m, s, n, z, and sc. So we have n still, s, and z, and it looks like that. And I think I forgot the s, right? Yeah. Whee. There we go, just like that. And so now we have all this stuff, and this is still what we have. Okay, so now what needs to happen is the question. So we have all of this. We essentially get this back, and we need some kind of application to take place. Where was our second argument? Because we still have that sitting out. Okay, that's what we still have. We still have, oh sorry, I think I did this there, but I meant to do it here. Excuse me. Let's redraw. First of all, maybe we can move this up. Whee. And then we can move this to here. That's good enough. Oh no. There we go. Okay, so we got to do that there, and we should also do it here on the second one. So let's also replace that with, let's just do it here. What does it need to be? Lambda, I don't know, p and q of ppq. Okay, and so now this one is the new thing to apply for n. Ready? So, dun dun dun, we have replacing n with all this stuff. We have lambda s, ooh, it's looking like a number, lambda z, and then we have the rest of this mess still to do. Lambda x, lambda y, x, x, y, applied to s, applied to nsz, which is, this is now n, right? So lambda p, lambda q of ppq. Beautiful. And remember, this is the body, right? This is all one big body. And so this eventually is going to make 4. And let me prove to you that it does. I guess we'll need a blank slide. There we go. Okay, here's what happens. Now we have to apply. We have to reduce it all as much as we can. Now we're reducing inside the body of this function. We can apply this to this, and then apply this one next. Okay, so now s gets replaced with x. Ooh, that's nice. That's nice. This becomes lambda s, lambda z. We have, let's see here. Instead of lambda x, lambda y, we have lambda y, and then we have s of y. Oh man, oh man. It is working. Slowly but surely it is working. And then we have the rest of this to be applied still. And is there anything I forgot? Yeah, I think I forgot the NSZ still here. This is the N, and I forgot the SZ still. That's what I was wondering about. So let's delete all those. And then we have this all applied to S and Z. That's the idea. That's what needed to change. Dun, dun, dun. So we have S and Z for this one. And so look what happens. Let's just hurry up and reduce this one too. So it's a bunch of these moves at once. That became this, and now we're about to apply it to. Let's reduce this one. It's just, okay, replace the S for P, replace the Z for Q. Look what number it made. S of Z. It made 2 for these variables. Isn't that so cool? It's like replacing variables with the ones that we wanted, the S and the Z. Okay, and then we put this into here. Oh man, oh man, oh man. It's replacing 0 with this, essentially. That's what's happening, because we have this to apply. It's replacing it for y, which is the 0 spot. It's just adding more numbers onto S lambda Z. This is finally 4. S of S of S of S of Z. Yay, which is equivalent to 4. Isn't that cool? All right, so that is numbers. I think you can take my word for it that we can have pairs of things, a pair of these two things. This is a pair of x and y. It creates like x comma y, essentially. If you want to get the first thing of a pair, you can apply true to the pair, right? If you want to get the second thing, you can apply false to the pair. And this can give you lists. So we can build up lists if we want, like the list 1, 2, 3. We can just call that the pair 1, 2, 3 with pairs inside of pairs. That's fine. And then the fun stuff happens. All right, how do we loop? How do we actually do a bunch of computation? How do we repeat ourselves? Are you ready? So here is the simplest looping function. It diverges, we say, because here's what happens. You replace this for x, right? This in the body for x. So I replace this whole thing for x. So it's just this twice. What does it become? The original thing. So this goes on and on and on forever. It remains itself. Okay? It diverges. It never produces any final answer other than this one, unless that was what you were looking for. So we say that this one diverges. It never gets close to any real answer. It's like an infinite loop. Okay? This one's the infinite loop. And then, okay, we can actually do real work. If we want to do real work, if we want to loop, we have to use functions, which means we have to use recursion, sorry. And the way that we do it is we essentially come up with what's called a fixed point of a function. Okay? So this is going to take way too long to explain, so I'm going to give you the overview. I would be happy to talk to you about this, though, outside of class. I would be very happy. So if only we had a function like this called fix, which takes some other function and does something really weird to it. It applies that function to the result of fix with the function inside of it. Isn't that weird? So if only we had this, we could define this kind of function, this function as this body, we could actually end up with recursion, because this kind of like brings another version of g in to the body. Okay, here's the idea. So this g represents kind of one step of the factorial function. Okay, this is how we can actually do arbitrary computation. This represents one step of the factorial function, I guess we can say. And I use so many symbols on this slide, it thinks that I am writing Portuguese. Isn't that crazy? I don't know if I can fix that at the moment. I think it's here. Yeah, I promise it's English. There we go. So this is like one step of the factorial function, because it like takes itself as the function. Okay? This is weird. If only we could define f as fix of this g, we'd end up with the actual factorial function. So I know this is a lot to take in, but let me give you the high-level overview, and we can go from there. So if only we define f as fix of g, then we can apply it to like 3 and get 3 times 2 times 1. Let me show this to you. And again, this is using our other stuff. So replace like if and else and 0 and 1 with all the stuff that we've talked about. It really is lambdas all the way down, but it gets a bit cumbersome, so we kind of go back to high level. But you can replace all of this with lambdas. And so let me try to apply f of 3, okay? That is fix of g applied to 3, which starts evaluating, okay? Because this, what's fix of g, that is, if we could do it, it would be g of fix of g, which is g fix g applied to 3, which becomes what this ends up being, all this stuff, because that's g, right? We're just applying this for r and this for n. Okay, so let's replace r and n with this and this. Okay, so we have if n equals 0, then give back 1, else we can do n, which is 3 times r, which is fix of g. Oh man, 3 times fix of g with fix of g as its other parameter. And then we have 2. Okay? So if actually the number that we gave was 0, we would finish. We wouldn't do the else case. We wouldn't have to do any more recursion. So we would be done, kind of. But we are not, alas. Let me give you the high-level idea as to why fix does its job, and it actually gives you recursion, if only we had a fix function. Because we're eventually going to get to the else statement, right? With enough ... dots. We're going to try to do 3 times fix of g of 2. And let me show you what happens, because what is fix of g but g of fix of g? Yeah? That is the whole point. That is the whole idea. 3 times fix of g becomes g of fix of g. And then we've got it applied to itself, which is another, let's just unapply that one. Let's keep it fix of g, and then we have 2. And look what happens to this one. G of fix of g again, it becomes this all over again. It's 3 times, okay, if n equals 0, then we give back 1, else we do 3 times this guy, fix of g, and then we have the 2 here this time. Dun dun dun. So let's see here. How do I want to show you this? I did skip a step. This is supposed to be lambda r, lambda n again. And if you apply that, we gave it n minus 1, so it's 1 now. 3 times, sorry, this is now 2, therefore. 2 times all this madness again. 2 times fix of g of fix of g, this time with 1. So it's getting smaller. It's getting to the answer. And eventually once it hits 0, it'll give back the 1 instead. Okay? So it's 3 times we hit the else times 2 times this answer. So that's my hand-wavy idea of proving to you that fix, this function, if we had a function that worked like this, that like applied g to itself, kind of, it would give us back the right answer. It would allow us to do recursion. Okay? Because we're like finding the fixed point of a function. That's what it is supposed to mean. Okay? So that is the idea. And I definitely don't have enough time for this, but I should say, if we have time, and we don't. Let's see how this evaluates to that. Maybe in Racket, in a future semester, I could do it a bit faster. But here is the magical thing called the Y Combinator, which maybe you've heard about. It's a fancy computational topic. And so it's like the most exciting, the most popular implementation of fix. There are multiple. And this one actually works, okay? If you say y of g, it evaluates to g of y of g. And that's what we wanted. That is what fix gives us, okay? That is the hope. Okay? So, yeah, that is everything that I wanted to talk about today. Hopefully this has, like, interested you. And now you know a little bit more about lambdas. So you know the lambda calculus now. Be free and use them in your programming languages because they're wonderful. You should be comfortable with it now, I hope. So yeah, that is all for this lecture, and I will see you in the next one, and we're going to make a new programming language ourselves. So I'll see you then.